In this sixth lecture on advanced quantum mechanics, today we shall discuss addition of angular momenta. The addition of angular momentum means it includes the addition of two orbital angular momenta. It may be the addition of two spin angular momenta. It may be the addition of an angular momentum of an electron with the spin of the same electron, like this, or it may in general be the addition of two total angular momenta. In our discussion with Dirac's theory Dirac's theory in central force field, we have seen that the orbital angular momentum is not a constant of motion, and one has to add a quantity which we call spin to get the total angular momentum, which is a constant of motion. So we encountered a situation where addition of angular momentum is required. Before going into the detail, we want to discuss one more point, that is the complete set of commuting operators. Complete set of commuting operator, that is CSCO, which leads to the concept of good quantum number. Let us consider an hydrogenic electron. Then we know that the each Hamiltonian commutes with L square and LZ operator. So if we consider the non-relativistic theory of hydrogen atom, then these three pairs of quantum numbers commutes in pairs. They commute in pairs, and you see that the wave function that we have obtained in the Schrödinger picture is NLML. N is the quantum number related to this, and these two quantities specifies L square and LZ. So if we consider the non-relativistic theory, these three quantum numbers are commutes in pairs, and they can describe the state of the system completely. We need not to know anything more. Every information regarding the system can be obtained from the eigenvalues of this operator. Remember that there is a restriction to the available knowledge imposed by the uncertainty principle. So we define a complete set of commuting operators as the minimal set of commuting operators, that is the operator which commutes amongst themselves in pairs, and which can describe the system state of the system completely, is known as the commuting operators. If this set, although is complete set when we ignore the spin, but whenever we can include the spin, this is no more a CSCO. Then we have to add L square, LZ, SS square and SZ. This is one way of representing this. Another way of so this could be a complete set, or we could have H, L square, SS square, J square and JZ. This is a favorite choice of complete set of commuting operators. Whatever be the choice, these five operators commutes in pairs, and we get the CSCO as this. With this knowledge, I come to the two situations where the addition of angular momentum becomes very important. Now we consider a two atom system. Two atoms, say for example, two atom system. So atom 1 and atom 2, initially they were far apart, and the Hamiltonian of the atom 1, if we consider one electron atom, then the Hamiltonian of ith electron I is equal to 1 or 2 minus h line square by 2 mu I V of Ri. This is the Hamiltonian of the ith atom, and I is equal to 1 or 2. We define the corresponding Hamiltonian is H1 plus H2. So this is the Hamiltonian of the system when the two atoms were far apart and there were no interaction between two atoms. In this case, we find that H0 commutes with Li square, and it also commutes with Liz. It commutes with this. Now we consider the situation when the two atoms comes closer to each other. When the atoms are in neighborhood. Then an interaction potential comes into play. This is the Hamiltonian now becomes H is equal to H0 plus H prime, some addition term, where H prime is equal to V of R1 minus R2. We have considered only the electron-electron repulsion term as the additional interaction. To be precisely, there are other interaction terms too. Say, for example, this is the proton 1, this is electron 1, this is proton 2, this is proton 2, and this is electron 2. So this Hamiltonian considers this interaction. This is included in V of R1. This is included in V of R2. When these two comes closer to each other, actually there are other interaction arises. This is due to the proton-proton repulsion, electron-electron repulsion. This proton interacts this and attracts this and there. So there are 4 more interactions. These blue colored interactions are included in H0, and actually H prime should comprise of 4 interactions. But in this case we have considered only this part. So this is this interaction only. And to keep the discussion simple, we have ignored the other parts. And this part is found to be very important. This part is found to be very important in the formation of hydrogen molecule. Now, if we write the Hamiltonian like this, it is found that H prime does not commute with L1Z. To be specific, it is found this is equal to L2Z with the minus sign. That is if we could define Lz is equal to L1Z plus L2Z, then Lz commutes with H prime. So we see that in this case the addition of angular momenta is required, and Lz is the z component of the resultant angular momenta. Let us take a very simple example of this sort. We define L operator is L1 operator plus L2 operator, so that L square is L1 square plus L2 square plus twice L1 dot L2. This is L1 square plus L2 square plus twice L1x L1y plus this is L1x, L2x, L1y, L2y, L1z, L2z. Now we consider the commutator of L square with L1z. Then this is L square L1z plus L2 square L1z plus this term 2 times Now L square commutes with this, so this is 0, and these two are not related, so they are 0. So we have to consider basically this term, of which this part commutes, so we did not require to consider this commutator, and we require to consider these two commutator relations. These are twice L1x, L2x, L1z, the first commutator, and the second commutator is L1y, L2y, L1z. Now this commutes with L2. L1 components of L1 commutes with L2, so we can write it as 2 L1x, L1z, L2z coming from the right. Actually we have used the commutator relation that AB commuting with C is equal to AC commutator B coming from the right, and BC commutator A coming from the left, but this part is 0, so this part is only there. Then L1y, L1z, L2y. This is twice. This part is minus IH cross L1y. This is L2x, and this part is plus IH cross L1x, and this is L2y. If we perform the calculation on this line, we say that we can show that this is minus L square L2z, what we said earlier. So we see that when such interaction comes into play, which we have considered here, electron-electron repulsion term, then we see that additional Hamiltonian that has to be taken into account. The z component of the individual angular momenta do not commute with the modified Hamiltonian, but if we define as resultant angular momentum, then its z component do commutes with the modified Hamiltonian. So we need for a addition or to find out the resultant of two angular momenta. Another example is coming from a single electron. Such situation also arises in case of a single electron. Consider an hydrogenic electron. Then it has spin angular momentum and orbital angular momentum. Earlier we have started from the relativistic point of view that one needs to add the spin and orbital angular momentum. We consider spin orbit interaction. Spin orbit interaction. Here the Hamiltonian, the additional Hamiltonian is some constant z e square m square c square 1 by r cube L dot s. We write it as some part xi of r L dot s, where xi is the part, z e square by m square c square on by r cube is the z part. If we can perform calculation in this fashion, we see that h prime Lz is equal to minus h prime Sz, which indicates, and not 0, which indicates that h prime jz is equal to 0. This is the situation. I am not performing the calculation, which is can be evaluated exactly in the way we have done it when we consider in the earlier example the addition of two orbital angular momenta. Before going further, I would like to say something about the spectroscopic symbol used for our orbital angular momentum. Sometimes we use the letter small lowercase letter L, S, J to represent angular momenta, and sometimes we use L, S, J, the uppercase letters. Which one should be used when? If we consider a single particle system, a single, say for the electron of the hydrogen atom, if we consider electron for single particle, means electron, then we should use lowercase letters to represent angular momentum and their quantum numbers. These uppercase letters are used for more than one electron, or for atoms. When we shall consider the angular momentum related to molecules, we will see that these are lambda, sigma, the symbols are used. Lambda for orbital to represent the orbital angular momentum of molecules, and this is the spin angular momentum of the molecule. These are the notations. So when we are talking about small l, that means this discussion is for one electron only. In that notation, the earlier calculation should be performed in terms of small l1 and small l1 square, l1z, l2 square, L2z, so that we finally define L is equal to L1 plus L2 and L1z is equal to L1z plus L2z. That should be the correct notation. So we now switch over to the general discussion of this. Before going to this, I would like to cite the earlier example, or this example may also serve the purpose. What is the physical reasoning? Say we are to form J, the total angular momentum, out of L and S. Generally, we know that quantum numbers J and Mj, so we know L, Ml, and we know SMS. These quantities are specified. So whenever we want to specify the orbital angular momentum completely, so we have to specify two quantum numbers, and for S we have to give two more quantum numbers. So if we see what happens pictorially, say this is the L. So L vector, and if this be the z axis, then we know its projection. So we know this value. This value is the value of L is equal to h cross L into L plus 1. This is the value, the length of the orbital angular momentum, and we know, say L is equal to 2. So this is for L is equal to 2. This quantity is root 6 h cross. So the vector has a length of 6 h root 6 h cross. And when we are considering the value of L to be 1, ml to be 1, this projection is simply h cross. But there is no restriction in which direction this will be oriented. So this may be oriented in any direction which have the same projection. And if we consider this to be the S vector, the same thing is applicable to S, and S can precess about this, so that its projection ms is half. ms is half. If the projection is negative, the angular momentum is directed downwards. This is the representation known as uncoupled representation, in which case the L and S are not coupled together. When we add these to get J, L and S we get J, then the situation is that L and then S, so we get this is as the J, this is L, this is S, so this is vector J. Recall that it has a component, its magnitude is h cross L into L plus 1. The magnitude of S, this is root over S into S plus 1, and this has magnitude root over J into J plus 1. And this L precesses about J, this L precesses about J, and S also precesses about J, and the resultant J precesses about Z axis. This is known as the coupled representation. Our aim here is to find knowing L and S value, that is, if we know the quantum number corresponding to two angular momenta, how to get the quantum number representing the resultant quantum number. So we consider a general case, the summation of J1 and J2 to J So our case is we know J1 and we know J2. So we know J1 MJ1 and we know J2 MJ2. Our aim is to find out J, which is vector J1 plus J2, so J2 in quantum mechanics they are operators, and Jz, which is Jz, which is J1z plus J2z. That is to know the quantum numbers for this J and for this Mj. This we know this, these are known, and we are to know this. How to do this? We may look upon the situation in a different way. We may see that these are the complete set of commuting operators J1, that is the operators, the CSCO to be J1 square, J1z, J2 square and J2z. This is that, and this is uncoupled representation. Uncoupled representation. Here we know J1, the quantum number J1, MJ1, J2 and MJ2. These four quantum numbers are known, and we want to switch over from here to another case where CSCO would be J1 square, J2 square, J square and J1z. That would be the and this is known as the coupled representation, which we have described here for spin orbit interaction. The quantum numbers for this is J1, J2, capital J and capital MJ. These two are known. Our objective is to know J and MJ. The actual theory, the mathematical theory is this bit involved. We are not going to this mathematical theory, but we say that this is done in such a way, the rule for getting J and MJ. 1. J max is equal to J1 plus J2. These are not operators, these are quantum numbers. J mean is equal to J1 difference J2. So J min, J max changes from there, and third is Jz is equal to Mz is equal to this should be Mj is equal to Mj1 plus Mj2, and the change in the third point is J changes by unity, J changes in unit step, in unit step. And how many these values will be there? There will be 2j plus 1 values, and there will be 2j plus 1 values, 2j plus 1 values of mj. This mj value, which one is smaller, j1 and of this j1 and j2, whichever is smaller, this capital J is related to the 2j plus 1 of the smaller one. That is, if j1 is smaller, then capital J will have 2j1 plus 1 values. If j2 is smaller, then it would have 2j2 plus 1 values. And these are the basic theory of LS coupling and JJ coupling terms. And now coming to the LS coupling scheme. In LS coupling scheme, they consider a multi-electron atom. Then it has electron number 1, 2, 3, 4, etc. Then in LS coupling term, in coupling case, the individual angular momenta is added up. So originally we have L1, we know L1, L1Z, L2, L2Z, etc. We have these operators. Individual electron, this is for electron 1, this is for electron 2, and we add L as summation over Li operator, sum over I over all electrons, and we individually add S, which is the sum of all spins of all electrons. Say we consider a 2-electron system. For a 2-electron system, two-electron atom, rather, then L is equal to L1 operator plus L2 vector operator. Say the quantum number corresponding to L1 is L1 and that is L2. Then this quantum number capital L is L, and L has values from L1 plus L2 to L1 difference L2 in unit step. Say for example, L1 is equal to 1, L2 is equal, as for a first example 1, L1 is 0 and L2 is equal to small l, in which case capital L value is 0 plus L only one value is possible, because orbital angular momentum number can never be negative. And here L1 is smaller, so the number of values of capital L is 2L1 plus 1, which is 1, so it has only one value. And correspondingly ML could have values from minus L to plus L, from minus L to plus L in unit steps. If we have L1 is equal to 1 and L2 is equal to 2, then the possible values of L would be 1 plus 2, 3, then 3 minus 1, 2, and then 1. So there are 3 values. You see that L1 is smaller, and its value 1. So capital L has 2 L1 plus 1 these values. As in third example, we consider L1 is equal to 3, L2 is equal to 2, in which case capital L would have values 5, 4, 3, 2, 1, because this is L, this difference. So here we have 5 values. Here you see that L2 is smaller, and we have 2L2 plus 1, 5 values. Coming to the spectroscopic notation, in for atomic electron, if we have L is equal to 0, we say it's S state. For 1, we say P state. For 2, we say D state. For 3, we say D state and F state. If correspondingly, if capital L is equal to 0, we call capital S state, capital P, capital D, and this is 3 capital F. Now coming to the addition of spin angular momentum. Spin angular momentum, we have for the same 2 electron system, S is equal to S vector operator is equal to S1 operator plus S2 operator. You see that this is specified by S1 and MS1, this is S2 and MS2, and this is, and we are to specify S and MS of it. Oh, here we have missed this ML1, ML2, and we need to know ML. So as per this prescription, the values of S lies between S1 plus S2 to S1 difference S2 in unit steps. So for electron, these are half, these are half. So for 2 electron system, this could be 1 or 0. Here S1 and S2 both are same, so we have 2 into half plus 1 is equal to 2 values of S. For this value of S, we have MS could have values 1, 0, minus 1, and for this MS has a single value there. Now coming to LS couplings became. These are the individual, here we have added the individual angular, orbital angular momenta to find out the capital L, the resultant one, and individual spin angular momenta to get the resultant of spin angular momenta. In LS coupling scheme, now we define J operator as L operator plus S vector operator. Again, this is specified by L ML value, this is specified by S and MS value. We are to know J and MJ values. For a given value of L and S, J ranges from, as per this prescription, J ranges from L plus S to L minus S, and for a given value of J, MJ ranges from minus J to plus J. So we demonstrate the scheme in a tabular form. We consider a case that is in which case L1 is 1 and L1 is 1. We consider a case L1 is 1, S1 is half, L2 is 2, L2 is 2, and S2 is again half. So addition of two things. So we define L capital L, the quantum number corresponding to resultant orbital angular momentum, this is L1 plus L2 to L1 difference L2, which is in this case 2 minus 1. So this is 3, 2, 1. These are the states. These are the values of capital L, the quantum number of total orbital angular momentum. Similarly, this has S1 plus S2 to S1 difference S2 values, which are 1 and 0. So we are to find out J and Mj out of this. So we write a table L1 first, S1, S2, rather we write S values, L values, say S value is firstly 0 and L could have values, S is 0, L could have values 3, 2, 1. This is, and for these J values are, J values is L plus S. S, if we consider S0, so J values are 3, 2, 1. Spectroscopic notation, if we coming to the notation, this notation is generally we denote a number J, number which is this number which is obtained from this. So if 1 it is S P state, if 2 it is D state, if 3 it is F state. Then we write the J value on the right side. So J value is 3, 2, 1, and here we write 2s plus 1 multiplicity. So this is 1. These are called singlet state. So basically a letter X, J value, and this is 2s plus 1 values. These are the state notation. Now we come to the value now we write S is equal to 1. Now for L is equal to 3, L is equal to 3, there will be 4, J value will be 4, J value will be 4, 3, 2. Because if we add 3 plus 1 is 4 and 3 minus 1 is 2. So we have values from 4, 3, 2. 4, 3, 2. So since it is 3, this is F state. F 4, 3, multiplicity is 3. Then this is F 3, 3, and this is F 3, 2. Then coming to L is equal to 2. For L is equal to 2, it is 3, 2, 1. Since L is 2, it is D state. So this is D, D, D. The states are D. J values are 3, 2, 1. They are triplet states, as S is half. And L is finally L is 1, then it is 2, 1, 0, 2, 1, 0, and the notation is L, which is from P, 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 the 3 states are P, the J values are 2, 1, 0, multiplicity is 3. So these are the possible states that can arise from a combination of this. Now we're coming back to the JJ coupling scheme. In JJ coupling scheme, the J quantum numbers, the individual we are taking again considering the same example in JJ coupling scheme. We first define L1 and S1, these vectors are known, and from this we get J1 total vector is L1 vector plus S1 vector. So in this way, J1s are first constructed. Ji is equal to Li operator plus Si operator. Then we get capital J vector operator is the sum of Ji vector operators. This is the scheme. Now we apply the same theory. L1 is equal to 1, L2 is equal to 2, S1 is equal to S2 is equal to half. So J1, we first construct J1. So the tabular form, since S1, L1, S1, J1, and we need not to make this table so complicated. So J1 values is, J1 value ranges from L1 plus S1 to L1 difference S1. So this is L1 is half, so these values are 3 by 2 and half. And similarly, J2 value is L2 plus S2 to L2 difference S2. This is L2 is 2, so this is 5 by 3, the 5 by 2, 3 by 2 and a half. You see, among here L1 is 1, so S1 is half, sorry, so we have two values, 3 by 2 and half. Here we have messed up. 2 minus half is 3, so S is half, so we have only two values. So we make a table J1, J2 and J. And for each J1, capital J will be determined by, as in the case of coupling scheme, we consider J1 is equal to half, J1 is equal to half, and J2 is equal to 3 by 2. Then J values, if we add these two, firstly we see that there will be two values, so these are, when we added it, 2 and 1, sorry, 2 and 1. Then this is half and this is 5 by 2. Again here we will have two values and they are 3 and 2. Now we come to J1 value is 3 by 2. J1 value is 3 by 2 and this is 3 by 2. So these will have 3 by 2 multiplied by 2 into 1, 4 values. These 4 values are 3, 2, 1, 0. This value, when we add these two and when we subtract these two. And for J is equal to 3 by 2, 5 by 2, we will have again 4 values, and when we add these, this is 4, 3, 2, 1. These are the values of angular momentum total angular momentum quantum number capital J as per the JJ coupling scheme. So that's all about the how to add to angular momenta. Our main objective is to get the quantum number corresponding to angular momentum.